So yesterday good morning everyone. I welcome everyone for the third day for one session. We have you can say lecture followed by a tutorial. After the session, I will take you to the laboratory where the live demo of ammonia production, plasma technology will be explored to the participants. And here, the total information, environmental benefits of regarding transportation. So here we are going to talk about, I can say, the role of engines on handling hydrogen and ammonia. I hope few of them are not aware of how the engine works. So, as you all know that engine is a device which can convert chemical energy of the fuel. It can convert chemical energy of the fuel into thermal energy, we call it as a heat energy, followed by the heat energy into mechanical energy. So the chemical energy is the stored energy actually. It's nothing but the stored energy which is available in the fluid. So how much you know that for diesel, we are dealing with majorly with can say for heavy automobiles, we are dealing with the diesel. So it has a calorific value. Calorific value, or you can say energy content of the fuel in terms of I can say megajoules per. If you burn 1 kg of fuel, it's going to produce about 43 megajoules per kg. If you burn the petrol, we call it as petrol here. In the US, it's called gasoline. They simply say gas. So the calorific value is about, maybe I can say, nearer to 45 megajoules per kg. So if you burn 1 kg of the fuel, you are going to get a thermal energy. If you burn diesel, you will get 43 megajoules. If you burn petrol, you will get 40 megajoules. Right? You need the burning mechanism inside the engine to burn the fuel. So as you all know that in order to do the burning or combustion, combustion is nothing but an oxidation process where the fuel reacts with oxygen along with nitrogen to produce as the flue gas. The burned product called flue gas. Here we have the heat. So here the fuel is a hydrocarbon. Fuel is the hydrocarbon. When it reacts with the oxygen, right, it produces CO2 and water. If it is completely burned product, we are neglecting usually for all the school days. They are not talking about the nitrogen role in combustion. Simply say hydrocarbon reacts with oxygen, produces CO2 and water. But nitrogen also will react. That's the reason why you will get an oxides of nitrogen. As per the Zeldovich mechanism, when the temperature of the reaction, the combustion chamber, if it is greater than 700 degrees centigrade from the oxidation of hydrocarbon and oxygen, there is a zone where the nitrogen also reacts with this oxygen. So we call it as nitrogen reacts with oxygen, produces nitric oxide. This NO reacts with oxygen again, it produces NO2. So the combination of NO and NO2, we call it as NOx emissions. Now, I am going to burn the fuel. So where I am going to get a thermal energy, assume that I am having 43 megajoule of heat available in the flue gas now. Right? Only heat is around available at high temperature. Maybe around the temperature is more than 2500 degrees centigrade after burning. But what about the pressure? Combustion nothing but explosion. As the volume is closed, volume is fixed. It's a closed system. So during burning, it tends to increase the pressure. Normally, depends on the different load condition. Suppose we are operating the engine at no load. That means no one is occupying, only engine is alone running. You will get, I can say, the pressure in case of diesel, I'm telling, it is about maybe I can say 40 to 45 bar. When the load is applied, you are injecting more fuel, right? Suppose if you have a two-wheeler, only one, no one is occupying the seat in the two-wheeler, the amount of fuel consumed will be less. So the amount of the pressure developed is going to be less. When instead of sitting two people, suppose 4 or 5 people are sitting, the load is increasing. The load is directly proportional to the increase in the fuel quantity. So naturally, when the load increases, the pressure will be getting around 75 to 85 bar. So you are accumulating the fuel, all the fuel has to be burned out before the energy can be developed. Okay. Now, you are creating the energy with high temperature and pressure. If the pressure, if it's not converted into, right, the mechanical energy, or it's not going to be expanded into the engine, you will not get the mechanical energy at the crankshaft. Okay. Now, because we are dealing with transportation, there are two types of, I can say, strokes are there. One is 4-stroke, another is 2-stroke. But some, preferably in marine application, they are going for 2-stroke because for every, I can say, 2-stroke, you are producing 1 power. Whereas in 4-stroke, we are, after completing 4 strokes, I talk about what is stroke, you will get 1 power. That means we compare the power developed by the 2-stroke engine. This means 2-stroke power developed is equals to 2 times the power developed in the 4-stroke. Power developed in the. That's why the marine shipping and all, they are going for 2-stroke. I will not much talk about the, can say, 2-stroke, as it has the, in terms of power output is okay, but in terms of emissions perspective, 4-stroke is better, right? So there are, we are saying 4-stroke. What is that? First one is suction. Suction is also called intake. Second one is compression. Third one, combustion or expansion stroke. Or we can even say power stroke. That is the only stroke. This is that is the place where the power is produced. Fourth one, you have to expel out the gas, we call it the exhaust stroke. But we may be telling that when if you see the schematic, you stand in front of the engine, you will have this kind of arrangement. This is the front view of the engine. This is the front view of the engine. It has several components. This is called intake manifold. You have the inlet valve. You have the exhaust manifold is the pipe which connects the flue gas, the exhaust pipe. So this is nothing but cylinder head. Head similar to a human being. We have a head. It's mounted on this place. It's called above that we have the head, which has the provision to keep valves, inlet valves, provision to keep the spark plug in case of petrol, fuel injector in case of diesel. Correct? Then we need a valve actuating mechanism which is attached to the valve to move the valve up and down during the suction stroke and exhaust stroke. For the remaining 2 strokes, both the valves are closed. Then, to transfer the energy which is available after burning into the crankshaft, we need a piston, we need a connecting rod which has a small two ends, one small end and big end. Small end is attached to the piston, big end is attached to the crank. From the crank, you are going to take it to the crankshaft. So this is called crankshaft. This is connecting rod. This is piston pin or gudgeon pin. So this is called crank pin. Okay. Now, there are four strokes are there. In terms of science, I'm telling you, people will say when the inlet valve opens, in case of petrol engine, both air and fuel will enter into the engine. It's not so. It's not so, right? If the valve is open, fluid will not flow just like that. It will see to the pressure outside and inside going to be have some difference. Right? The fluid will flow only if there is a pressure difference. So suction stroke. So I call intake stroke. You have the piston, you have the cylinder. Inlet valve is open, exhaust valve is closed. Let's say inlet manifold, exhaust manifold, IV, EV. Now you need to, during the suction stroke, the piston is at top dead center. Dead at the top. We call it as top dead center. Dead at the bottom is called bottom dead center. It may not move above that, it may not move below that. Okay? So during the suction stroke, the piston is at top dead center. That the distance between above the piston to the top of the engine, say, the cylinder head is called the clearance volume. We need some clearance to allow the valve to move up and down, but also to keep this valve plug in case of petrol or to keep the fuel injector in case of diesel engine. And you can see here, during the suction stroke, here in case of petrol, I'm talking about older version, not a new version. Fuel plus air, which is available after maybe you are mixing both fuel and air in the carburetor, fuel and air is available, ready to enter through inlet valve during the suction stroke. People will say like that, but it's not so. In order to allow the fluid from the atmosphere into the engine or from the carburetor into the engine, you need to create a pressure difference. You need to create a pressure difference. How to create a pressure difference? The good example for this, you are not feeling well, right? You have some temperature, maybe the temperature rise happens. So you are going to the doctor. Doctor says that I want to inject the medicine into your body. The good example for distance arrangement is the syringe. So keeping the syringe inside the bottle, automatically fluid will come. What is doing? Is pushing. Maybe I can see is pulling the piston to the other end. What will happen? The pressure inside the cylinder is going to be lower than the pressure outside. So due to the delta B, when you are increasing the volume from the original position, assume that this is V1, then you are moving the piston to V2, next volume. Then the volume increases, as you all know that when the volume increases, pressure decreases. Pressure is inversely proportional to the volume. Due to the increase in volume, because of the drop in pressure, always fluid will see whether the fluid is remain same, the pressure and here same, no fluid movement. And here the pressure is lower than this, fluid will try to. Because of that, the fluid is going to enter during the suction stroke. Up to what point? Up to the bottom dead center. The distance traveled by the piston from top to bottom, we call it a stroke. The length is nothing but stroke. The actual movement of the piston from top to bottom bottom to top, bottom to bottom, again bottom to top. There are 4 strokes are happening in the 4-stroke engine. Bottom top to bottom, 1 stroke, suction, bottom to top, compression, then again top to bottom, combustion, again bottom to top, exhaust. So during suction stroke, first stroke, inlet valve open, exhaust valve closed. During suction stroke, EV exhaust valve closed, inlet valve open. Whereas for the remaining 2 strokes, called second stroke, called compression stroke and the combustion stroke. So compression stroke means you need to compress the fluid. Whatever you collected, the cylinder up to the bottom dead center is available now. So when it reaches this position, the pressure inside, the pressure inside, pressure outside, both are same. There is no movement of the fluid. Right? Now you are going to close the valve, same level. You are going to close the valve, both inlet and exhaust valve. So now when the valves are closing, that this is valve, this is the valve. If you close the valve, what happens? The pressure accumulated, so the piston moves up. The piston moves up. What happened? What about the volume? Volume decreases. And the volume decreases. What about the pressure? Pressure increases. Because of the decrease in volume, you are increasing the pressure. So that pressure, in case of petrol, I'm saying. So due to the rising pressure up to this point, top dead center, the fluid will see correspond to the pressure, what is the temperature. Fluid, if it is automatically ignites by its own, it's called auto ignition engine. But petrol is a good fuel for mixing, but it's a poor in terms of ignition. So you need about 700 to 750 degrees centigrade to initiate the combustion. So that's the reason why they are using spark plug. Without spark plug, you cannot start the combustion. But people will say diesel is a bad fuel. No, in terms of combustion, diesel is a good fuel because doesn't require any spark plug. Only you have to inject the fuel during compression. At the end of the compression, you will see the pressure is about at no load 45 bar, at higher load is about 80 to 85 bar. That's what the pressure. We measure the temperature by putting some device. It is more than the ignition temperature of the fuel. So automatically fuel ignites. This is the fundamental principle. Okay. Have any doubt? The combustion. Combustion in petrol, in the earlier days, they are mixing both air and fuel actually into the suction during the suction stroke. Whereas in case of diesel engine, what they are doing? They are allowing only air, no fuel at the during suction stroke. Compression only air. At the end of the compression stroke, they are injecting the fuel over the high pressure, high temperature air. As per the pressure, the temperature is more, maybe again two times more than the ignition temperature. That's part of the pressure. So when the fuel is injected, it takes amount of heat from the air for evaporating, mixing and burning. So burning combustion is not going to be immediate in case of diesel, but whereas it is immediate in case of petrol because you already mixed fuel and air. Correct? Assume that you are buying milk from the vendor. So he already mixed water into it. Right? Already is there. So you can when you heat it, what happens? Boiling point of water correspond to 1 atmosphere is 100 degree. But when you mix the water with the milk, it's not 100 degree. It's more than that. Assume that you have only water. You are heating. So what is the boiling point? 100 degree. Now you are injecting the milk over this. What will happen? Milk will absorb the heat from the steam, from the water for evaporation. How much heat you need to provide for evaporation? It will take some of the heat from the steam, but drop in heat also, if you measure the temperature of the total mixture, it's more than the ignition temperature of the diesel. That is the science. Even then, you are taking heat from the air by evaporating the diesel after dropping down, after completely converting the diesel into vapor. But even the drop in temperature happens. If you measure the temperature, it's more than the self-ignition temperature of the diesel. That's why ignition happened by its own. This is the basic difference. I will now move to the lecture. So the learning objectives for this lecture: explore the environmental benefits of using green ammonia as a fuel alternative in different transport sectors. Analyze the challenges associated with green ammonia adoption in transportation industry. Evaluate the potential of green energy, green ammonia to transform sectors in like shipping, aviation, and heavy vehicles. So here, introduction to green ammonia and transportation, we have covered already. Environmental impact of green ammonia we are going to discuss now. Then some case studies also we come across, but it's not related to the shipping, it's related to the stationary plant. Then future prospects and comparisons also I am going to discuss. So you all know that green ammonia is produced from renewable source without emitting carbon footprint. So it's called green ammonia. You can take either electricity from the grid or from the wind or from the solar. If you take the energy from these two components, wind power or solar, we call it as the green hydrogen or green ammonia. If you're taking the power from the conventional thermal power plant or from the gas turbine, then we can say it's not a green ammonia. It is maybe I can say if you use coal as a fuel for producing electricity, it's called grey ammonia. If you are using, I can say natural gas methane to produce ammonia, but you are going to capture some amount of carbon dioxide from the carbon capturing system, then it is called blue ammonia. If you are producing ammonia through the green route from the wind or solar or geo or tidal or wave energy, then the form of ammonia comes out is nothing but green ammonia. This is given here. So grey ammonia, maybe we can say it comes from the coal as a source. Ammonia orange, I can say it's from the nuclear. So the energy taken from the nuclear plant is called, if you are producing ammonia, then it's called orange ammonia. If you are producing the ammonia from the coal, or you can say it is grey ammonia, or coal, or the oil or natural gas without capturing CO2, also you can say grey or black ammonia. Then blue is whatever may be the system, natural gas or oil or coal. If you capture the CO2 in the exhaust, that's called blue ammonia. Ammonia only there, no carbon at all for the conversion of, I can say, water into hydrogen, hydrogen to ammonia. No CO2 you are producing, then it means it's a green ammonia. So transportation sectors is producing major CO2 emissions. You can see here, transportation 23%. Electricity conversion, we are producing 26. Then industry, they are consuming about, they are polluting about 28% out of 100. Building sector, they are producing 6%. Agriculture, they are, I can say the sector, they are producing 70%. So out of 100%, you can see that the major contributors are thermal power plant or whatever may be the way electricity produced from the hydrocarbon fuel. It's producing 26% CO2. Industry, steel industry, cement industry, leather industry, whatever may be the food industry. So whatever the way they are consuming hydrocarbon to produce some kind of whether it's a heat or power, they are producing 28%. The statistics of fuel consumption emission by transportation models, you can see here. Out of the transportation for under different sectors, 72% of the CO2 comes out from the road transport. Even that 72%, you can see here, the distribution is given here. The motorcycle, only 1%. This is for European Union. Then the light duty trucks, about 11%. Heavy duty trucks, another 27%. The remaining, maybe heavy trucks and other things. Then the transportation, you have railways also. Railways, they are producing about 0.4% because all the rails nowadays is converted to electric way of running. So the amount of CO2 is not coming. Anyway, we are consuming electricity, but how the electricity comes out, we need to check to find out the life cycle analysis. Then it may not be, that is for railways also. Then the civil aviation, aircraft application, they are whether it's carrying the passengers or carrying the load, the amount of CO2 comes out is 13.4%. Then water navigation, through the shipping. So they are going to carry the, I can say, most of the, I can say, the goods are transported through the shipping only. So the amount of CO2 comes out is also 14%. Now the Indian Maritime Organization (IMO) is also seriously working on it to use the ammonia in the for the transportation of the, I can say, for use it in the engine. So chemical composition, yesterday Professor Hu also pointed out to break, I can say, nitrogen into N2 into N. It's a triple bond structure. So you need high energy for breaking. So for breaking the nitrogen, it takes about, I can say, 30 to 40% of the energy needed for producing the ammonia. So is there any mechanism to, I can say, to break the nitrogen? Instead of even yesterday I discussed one of the faculty member in chemistry. So instead of using nitrogen, can we use some other form of nitrogen so that the amount of energy consumed for breaking the nitrogen going to be reduced? He also suggested that go for nitrates or something. Nitrate based component, then the amount of energy needed for breaking the nitrogen, because you need only nitrogen, other things you can eliminate. That also you can think about in the future research. Instead of using nitrogen and separating out, because separating out the nitrogen oxygen also you are consuming power in the PSA, and breaking the nitrogen or to react the nitrogen with the nitrogen and then breaking the ammonia into nitrogen and again the hydrogen, you are spending a lot of energy. So you can find out the way of nitrogen comes into the structure through simple means, and very energy, it's an energy intensive process, but it may be 50% of the energy needed for breaking the nitrogen. You can think about it. So we need to work on it. Find out instead of using nitrogen, is there any mode of use breaking the nitrogen to produce the ammonia? We need to really think about that. So energy density, you think you can see here. If you burn one, I can say, if you want to, in terms of energy density, I tell you, at 18.6 megajoule, ammonia having 18.6 megajoule, whereas the traditional fuel, diesel is about 45.5 megajoule, but it is, I can say, higher than the hydrogen content. Always we are, whenever the new fuel comes into the running the already existing vehicle, we always compare the new fuel with the conventional fuel, what exactly we are using. So you can see here, the hydrogen, in order to move any vehicle or to move the ship, the amount of energy needed when you compare with the LNG, assume that you are providing 1 kg here, here you need to provide 1.9 kg. So assume that you are carrying 1 kg LNG to move the ship from one place to another place. If you are switch over from LNG to ammonia, you can carry 1.9, about 2 kg to reach the same distance. Hydrogen, the same distance we want to reach, you can carry 2.5 times, because the molecular weight is comparatively low. Then that's the reason why the hydrogen vehicles are failed in an automobile, because instead of carrying the goods or instead of carrying the passengers, who are carrying more weight on the hydrogen cylinder. So automatically, when the load is not only from the, I can say, passenger, it is also whatever with the component associated with the automobiles is also not just the load. So when the load of the cylinder also increases, the fuel consumption dropping down. Then you can see here, it has some, I can say, advantages. Only thing, when you compare to the hydrogen, it is only 2 kg. So out of 2.5, and also you can see here, the pressure in which hydrogen is stored is 700 bar. 700 bar. So that means it's something like a pressure vessel. The thickness of the cylinder is not going to be comparable with the thickness of the ammonia cylinder and LNG cylinder. Here the pressure of the ammonia stored is about 20 bar, 10 to 20 bar. Here it is approximately, I can say, 30 times more than the pressure you are going to store into the hydrogen. So the weight of the cylinder increases because of maintaining the higher pressure to maintain the energy density of the particular fuel. And also you can see here combustion temperature ammonia is 651 degrees centigrade compared to 210. So what do you understand from this? Not to run the engine, if you want to run the ammonia and diesel engine, diesel fuel will run without any spark plug. But if you want to run any fuel, which is more than the self-ignition temperature diesel is designed for that engine. Diesel is designed for running diesel fuel. Suppose you want to replace that fuel, right? You run it with, I can say, ammonia, or suppose you are having some pyrolysis oil, there you can find out what the temperature at which the fuel can burn. So you can try it, the fuel can able to burn it well and good, if not able to reach corresponding to the comparative ratio of the engine. If it's not reaching about 500 degree or 600 degree, then there is no, the engine is not called auto ignition engine. So you need some kind of combustion enhancer. Normally you can go put a glow plug, but normally for alcohol engines they are putting glow plug, something like a heater they are providing, or you can put some kind of spark plug to initiate the combustion. So if you want to use ammonia and petrol, already spark plug is there, no issue. If you want to use ammonia in diesel, either by you are injecting ammonia, the form of gas, into the intake manifold like the petrol engine, or you can suppose the ammonia is in the form of liquid, you can inject it like diesel, but ensure that the temperature you need for initiating the combustion is about 651 degrees centigrade. So naturally convert the diesel engine into petrol engine. Okay. So the modification of the engine depends on what fuel you are dealing, and what is the temperature you need for burning that fuel. That plays a major role. So for that means you want to run the ammonia and petrol engine, no modifications are required. You can either, this already we have a carburetor, like like any LPG or other things, you can mix the ammonia if it is in the gaseous form. Or if you want to inject in the liquid directly corresponding to the temperature or the pressure you are maintaining the ammonia, maybe you can say you can inject, you need only, not only you need a spark plug, you also need a fuel injector in the petrol engine. Petrol engine, you have to attach with, along with the spark plug, fuel injector. The fuel is in the form of liquid. Whereas if the fuel is in the form of gas, you can directly inject into the intake manifold. The diesel engine, you are providing excess air, about like I say 50 to 60% more than the stoichiometric air. So if you mix up plenty of ammonia, it's not going to create so much of issue. Actually, if you see the exhaust of the diesel engine, except oxides of nitrogen particulate matter, you can see carbon monoxide emissions, then the hydrocarbon is not going to be much higher than the petrol engine. Because we are not limiting the oxygen entering into the diesel engine, whereas the petrol engine, we are controlling the both fuel and air. Naturally, the amount of oxygen entering for combustion, the maximum value is stoichiometric gas fuel ratio for petrol. Whereas in case of diesel, we are providing, suppose that we want only 14.5 kg of gas for to burn diesel fuel, but we are providing at some load, at no load 100 kg. So that's the reason why the emissions like carbon monoxide, hydrocarbon comes down in the diesel engine is very, very good. Because we are providing, at least I can say, nearer to 7 to 8 times more than the oxygen requirement diesel. In terms of safety also, as it has high ignition temperature, so even if you transport it, even if you find out the temperature is more than that one, then no problem for transportation. You can use, because that is 2 to 3 times more than the nice. So storage and transportability here is stable in liquid form. Ammonia ability to remain a liquid under manageable conditions makes it ideal for long distance transport and storage. But in order to store the ammonia in liquid form, you need a cryogenic tank. You need a cryogenic tank. So not like how they are transporting the petrol or diesel, doesn't require any cooling agent to maintain it. So the total cell should be covered with the refrigerant to maintain the low temperature. But not like hydrogen. Here, converting ammonia to hydrogen equals energy. That's why I said you are consuming a lot of energy to break the ammonia into nitrogen to hydrogen. So energy loss is going to happen. However, ongoing research aims to improve the catalytic process that can release hydrogen from the ammonia. So the catalyst part plays a major role for, I can say, to provide minimum energy for forming the ammonia and also for breaking the ammonia into nitrogen and hydrogen. So overall working in the catalyst part, then you can think about the catalyst which can able to use it for the green ammonia generation, because this is the future. This is the future. And how the Haber-Bosch people are saying you can go for Fe2O3, it is a catalyst, a proven catalyst. If you have some work on that, and you can prove that what Haber-Bosch did, you can prove that try several catalysts or global, I can say catalyst metal or non-metallic components or the catalyst can be generated from the different waste materials. Think about that, but you have to prove that your catalyst at least it produces equal to the paper Bosch or is better than the catalyst so far is available in the literature. It has a lot of scopes. Catalyst what plays a major role because that is going to reduce the activation energy of the energy needed for activating the process going to be comes down if you use the right catalyst. Yeah, combustion I already discussed. It is ammonia at high ignition temperature than the traditional fuels, which requires specialized combustion technology. Right? You cannot use ammonia in diesel or burning. So you need some kind of modification in the diesel engine to burn the fuel. You need to maintain when the fuel is entering into the cylinder, you need to ensure that the temperature inside the cylinder is more than 650 by using some kind of heater or kind of blow plug or some kind of technology what we are using in the petrol engine. You can put a spark plug, can initially create a spark externally so that the combustion is going to happen. So you need a modification. Using ammonia in diesel engine, you need a modification. Using ammonia in petrol, in terms of spark plug, it doesn't require any modification. But if you are injecting the fuel in terms of gaseous state, doesn't require any modification in the petrol engine. But if you are injecting the fuel, ammonia in the form of liquid, you need a fuel injector. But as ammonia is highly toxic as well as the highly corrosive in nature, because hydrocarbon, petrol or diesel is not corrosive. Actually, if you keep it for several years, it's not going to corrode. But if you keep the ammonia at the tank, you're going to allow into the injector for pressurizing the pressure to inject the fuel. So need whatever the pathway from the fuel tank into the pump and the filter, so many things, you need to put utmost care in design because it should be corrosive resistant material whenever the fluid is moving from fuel tank to the cylinder. Even the cylinder, you are going to inject into the cylinder, is made up of, I can say, aluminium alloys, piston. So aluminium is prone to corrosion, so that also we need to change it. You need to go for a specialized coating over this for anti-corrosive coatings over the cylinder component, engine component to take care of the corrosive fuel. Okay. So no carbon emissions, but NOx formation, because you are not only providing nitrogen from the air and also you are providing nitrogen from the fuel. So NOx formation usually happens in two ways. One is called fuel NOx, another is called thermal NOx. So thermal NOx created based on the temperature and the amount of nitrogen present in the air. Fuel NOx presents because you are going to break the ammonia. Automatically, you are not only providing hydrogen, you are also providing nitrogen. So that nitrogen also will export in the combustion. So NOx emission going to be in compared with diesel, maybe sometimes more than that also is possible because of the nitrogen possibility of the diesel is going to be not as much as higher than the ammonia. So either you can, there is a mechanism available in the engine to control the NOx inside itself. After burning, also it can be possible. So the flue gas comes out through the silencer, right? If you want to control the NOx at the exhaust also, it is possible. But what method we are following for controlling the oxidation nitrogen and the cylinder itself, during the combustion itself? So we go for EGR. Exhaust gas recirculation. So whatever the gas comes out from the engine, some percentage can be 5 to 10%. Right? It goes to the mixed with the intake manifold because the presence of inert gases, CO2 and nitrogen, is going to reduce the oxygen quantity when it mixes with the inlet air. They reduce it because NOx formation mainly due to oxygen availability, temperature during the combustion, that's specific. So what are the ways you can able to reduce the temperature? Is reduce the oxygen. Reduce the oxygen, automatically temperature will come down because when you are providing 15 kg oxygen, if you provide only 13 kg oxygen, automatically the temperature of the zone will come down. So when the temperature goes down, NOx goes down. You want to reduce the NOx to zero, operate the engine lower than 700 degrees centigrade. NOx formation is not going to be there, but you need to pay penalty for efficiency. If you have more temperature, all the hydrocarbon and other things will be burned out. So if you reduce the NOx, reduce the oxygen,
particle will increase, smoke will increase, hydrocarbon will increase. Carbon monoxide, NOx is very dangerous gases compared to the CO2. So that's why we are saying non-oxides of nitrogen and particulate matter or smoke both are enemies. If you reduce NOx, this will suit up. When you reduce particulate matter or smoke, this will. So when the temperature is more, suppose finding out for diesel temperature is around 2000 degrees centigrade, will have some value. Now you are going to take the ammonia, temperature is 3000 degrees. From the temperature itself, you can able to understand now NOx is going to be higher at the exhaust. So it's direct indication of NOx levels. Correct. So advanced technologies are available for diesel engine. They are called diesel particulate filter. It's available. Whereas for petrol also, we have three-way catalytic converter. Now the new for diesel engine, we are proposing selective catalytic reduction, injecting urea. Even the can say the urine what we are producing or the animals are producing, that urea also can. That is not urea, right? So we can inject it there. That also people try. So what are the ways you can able to reduce the temperature that will lead to reduction in NOx? But whenever you do some research in engine, you cannot reduce NOx to zero because it is directly proportional to the efficiency. If you bring NOx to zero, efficiency is going to be very, very good. Up to 700 degree, that is no formation of NOx. Above only NOx form. So after 700 degree, find out the corresponding temperature, the efficiency is going to be. For diesel engines are about 28 to 35% efficiency. If you run it without any disturbance. If you reduce the NOx, it goes to 15% or half of that. The efficiency goes down, the economy also affected. So this is the most important table. We can say the heating value, gas fuel ratio, flammability limit, laminar flame speed. The lower heating value, you can say for 1 kg, with respect to liter, it will be different. With respect to mass, it will be different. Okay. So you can say among this one. So this diesel and gasoline, maybe you can see methanol. Methanol is maybe around half of that approximately, maybe lesser than that, diesel or gasoline. Methane, but to store 1 kg hydrogen, you need a bigger cylinder. So it is blocked with respect to mass. But store 1 liter of diesel, you can carry 1 liter water bottle. But if you want to carry 1 kg of, I can say hydrogen, you need to carry n number of cylinders. Okay, we are not talking about cylinder weight, we are talking about the gas weight. The molecular weight hydrogen is the lowest among the periodic table, so you need to think about that. So air fuel ratio, stoichiometric air fuel ratio for hydrogen 34. If you want 1 kg fuel, you need to provide 34 kg of air. You want to burn 1 kg methane, you need to provide about 18 kg air. You want to burn methanol 1 kg, you need to provide only about 6.7 kg. Yeah. So gasoline 15, diesel also 15, ammonia 6.96. That means what you are infer from this? Anybody? What you are infer from?
Their intake is very less.
So yeah, intake very less. Stoichiometrically, I'm telling this one and this one have very low value. But for hydrogen, you need very high value. So if you want to do modification for diesel, it can take 15 kg as per the system design. But if you want for 34, you take a diesel engine will suck 15 kg air during suction stroke. You convert it to hydrogen, so only 15 kg is entering. Need to double it. So need a supercharger. Some kind of concept need to bring it at the intake side to force the air so that if you see some videos in Japan, right now the people are traveling in train. There is a person available, he will push it, maximum people. So you need some pushing mechanism in the intake manifold side to allow the 35 kg to burn 1 kg of hydrogen. So that's the reason why we are using supercharger, turbocharger to compress it to high level, maintain at same temperature by putting a cooler. It's called turbocharger. But you need to ensure that. Okay. But if you want to use methanol or this one ammonia, the existing system itself going to give 2 times more than that. Clear? Already is giving 50. We need only 6 kg. So that means combustion is going to be perfect. Below the flammability limit, you can see here, flammability limit, it is in terms of volume percentage, here it is 15 to 30, somewhat safer. Very low values going for the hydrogen, 1.5 to 75, then this is diesel is 1 to 6, gasoline is 1.3. How much it can able to travel? So it's called flammability limit here. Disperse it, okay, with the air. It takes a lot of time to use ammonia, whereas for other fuels, maybe assume that 4.5, 5. So almost everything same. The lowest is going to be for gasoline. The one more thing is having our flame speed. It is very, very important for burning in terms of burning. You can see here, it will take per second how much the distance it will travel. Very dangerous speed. Within a second, it travels 210 centimeter distance. When you create the hydrogen flame here, it will travel almost, I can say, 210 centimeter. That means about 2 meters, right? About 2.3 meters. The flame is generated, it will immediately reach 2.3. Whereas if you burn ammonia, the distance only 7 meters.
7 centimeters.
7 centimeters. Safer one. Even if the ammonia is getting leaked, combustion is going to happen, you can easily quench the flame immediately. Because the travel distance is less. But for others, it remains same. Methane 38 centimeter, 40, 52. But the lowest one is difficult propagation. Auto-ignition temperature you can see here. About methanol 465, gasoline 275 people are claiming. Then the ammonia 651. You can see here for all the fuels, 5 there. Hydrogen, methane, and ammonia remain same. But you want to use this fuel in the engine or the methanol also. Some modifications are required. You need exactly, I can say to initiate the combustion, you need a spark plug. If you are using liquid, methanol is a liquid, you can use the fuel intake. You cannot use the methanol in the intake because methanol is having a low, I can say. It has a poor, I can say, it is going to cool the charge very quickly. The leakage is the biggest problem in handling the methanol cell fuel. Octane number is a knocking tendency. You can see here, if any fuel, any fuel you are finding out, which has a knocking value, you can see here 120, greater than 120. That means the safest fuel. It will not create any sound. Knocking nothing but unwanted vibrations created during the combustion. So the value of knocking octane number is more. So even the gasoline is having the value of 88.9. You can see that when the petrol engine runs, we cannot feel whether the engine is running or not. So here you can see hydrogen is more than the diesel, petrol. Methane is more than the petrol. Ammonia is more than the petrol. So you cannot have the feel of the engine is running. Right? Whereas the diesel, diesel starts, that's all. It's going to create a sound like anything. It's more than the 50 decibel. Adiabatic flame temperature is nothing but the maximum temperature. It is going to be comes out after the combustion, after burning. You can see here, because of the higher laminar speed velocity, it is going to create a maximum temperature, 2500 degrees centigrade. After maybe the maximum temperature during the combustion you are going to get. If you assume that the systems are isolated, the adiabatic, no heat loss from the system to the surrounding. So the maximum temperature you are going to get for hydrogen, followed by gasoline, then methane, methanol, the lowest one is for ammonia. So quenching distance, what is you mean quenching distance?
Cooling distance.
It will flame will extinguish. 0.64, they will extinguish. It reaches 7 mm, then only it will extinguish. Quenching distance means you need a more time for quenching. Okay. So here, the quenching distance, it can easily go due to the higher laminar flame speed, it can go and touch the place and it will easily, you can say, quench. The latitude of vaporization, you can see here, it is 400, it is 461. Suppose you want to use this fuel here in diesel, no issue at all. Because it is 1-3 times the diesel, and also you can see here approximately equal to gasoline. So modification, much more necessary. If you want to use ammonia here, you want to use it in diesel, you can use the spark plug. If you want to use it in petrol, you can use the fuel intake. So application in terms of energy density. So we can use this one for shipping, industrial power, so that it can easily storable, comparable energy density with other kind of renewable fuels. Diesel and gasoline continue to dominate small scale, high energy demand scenarios on road transport. Cannot use ammonia or hydrogen, people are suggesting. You can allow gasoline to diesel to go on road transport for small vehicles due to the immediate combustibility and energy density. But innovations in ammonia utilization, such as hybrid ammonia hydrogen engines, are merging this gas. So for small transportation, it takes so much of time, right? So when you keep the vehicle on the road, right? If you allow to, I can say, to do the modification, if you allow the engines to start late, right? Lot of time. That this may not be suggested for time being. But in order to use ammonia to bring it to the like what petrol engine and diesel engines are performing, you need some kind of modification. You have to design an engine specifically for to handling ammonia and hydrogen, rather than modifying the engine, the petrol or diesel to suit the hydrogen and ammonia. So we have the attributes of key attributes of ammonia is a shipping fuel. Carbon intensity, there is no possibility of carbon dioxide comes up. So it complies the IMO, Indian Maritime Organization. Then L2O is producing high NOx emissions. So need to take work on that, how to maintain the NOx level, what is suggested by IMO. The energy density is about 18.9, approximately one third of the diesel. So if you want to use this fuel, you want to carry the, you want to increase the tank capacity by 3 times. You are carrying, if you want to reach Chennai from Trichy, maybe assume that per kilometer you are getting around 10 per kilometer reaches, you can able to travel 10 kilometers, maybe 350 kilometers. So you can charge 35 liters of diesel, the fuel tank. But if you want to use ammonia, it's about, I can say, 1/3. So you have to fill about 35 multiplied by 3 will get around more than that. So you have to reach the same distance by using ammonia, like petrol or diesel. You have to fill 3 times the petrol or diesel. Safety, as it has a low flammability index, no problem in terms of safety, and ammonia can be stored at higher temperature compared to LNG. So storage, you cannot have the ambient in our Trichy or the place where in some places in India you cannot reach, I can say, minus 20 degree, 22 degree. So whenever you want to carry the ammonia, when you want to operate at the ammonia tank at minus 20 degree, there's a possibility of heat losses, infiltration of the heat going to happen. So you have to properly insulate the vessel before carrying the ammonia in the form of liquid. Okay. You need a kind of cryogenic kind of tank you need to carry the ammonia in liquid. So shipping fuel comparison, heavy fuel oil 40.5, LNG 50, methanol 20, ethanol 26, ammonia 18.7. So relative tank volume I said right. So if you use heavy fuel oil, assume that tank volume is 1. Right. If you go for LNG, it's 1.6, methanol 2.3 times, ethanol 1.7 times, ammonia said 3 times. So you are going to use the fuel, but energy value, about 1 kg of fuel, you are getting only 1/3 of the value. So increase the quantity by 3 times. So you cannot use the same fuel tank to 35 kg diesel tank to reach, I can say, Chennai by using ammonia as a fuel. You will be end up after reaching Paramulur or maybe reaching the Ulundurpettai, the fuel will be going to be exhausted. So you need to ensure that based on the calorific value, how much the size I need to carry. Okay. Key projects in the field of ammonia usage in marine shipping. The man is yesterday we saw on video that the company man, right? They are working on a special new engine specifically for running the I can say ammonia. So the ammonia investment is about $5 million American dollar to develop the first ammonia fuel two-stroke engine by 2022 and commercialize in shipping. And there are several similar to that. There are several things also happening across Norway, Europe, and Japan. Japan they invested a huge money. A joint R&D agreement for the commercialization of ammonia fuel ships, including gas carrier and and barge of offshore bunkering and the use of ammonia poses certain challenges for adaptation to marine industry. High toxicity, erosion present the technical challenge I said already. Bunkering solutions for ammonia shipping fuel is not yet mature. The companies in the industry are looking to come up with solutions in the field. Only multiple companies are in process of development of ammonia-based engine. Ships will clearly have to re-engineer to run ammonia, which creates major complications. And today there is a little, if no use of ammonia fuel in commercial shipping. So market adoption is subject to technology, development time, and might be slowed down due to long life cycle of existing vessels. So these are the different parameters. You want to commercial viability of using 100% ammonia versus coal-based generation. This is the thing is available. You can see here. Now to produce green ammonia, 1 megawatt power, you need to spend 432, I can say, megawatt hour. Cost of 1 megawatt including carbon tax. So I can say 432 billion USD. Right? So you need to spend. Then for coal, 37. Same, I can say their energy input they are telling. Then the green ammonia in 2040 they are focusing there. This is blocked in 2022. So 2022 the estimation is about 432 billion USD to produce 1 megawatt from the ammonia. Coal, they have put 37 billion USD for 1 megawatt. Then you can see here the green ammonia in 2040 they forecasted that the amount is going to be invested. It is the same level, going to be 130, 192. That shows that they are going to bring a new technologies to reduce the cost of the capital cost of the fund money they are going to invest for producing 1 megawatt power through ammonia. Similarly here, the same amount of the energy production as we are comprised with the green energy, as the depletion of the conventional fields are happening, the cost of the fuel going to increase. So this increase from 37 to 191, 24. So that means about maybe I can say, or maybe 5 times the cost is going to increase if you produce 1 megawatt power through the coal because there's no coal available at that time. That shows that there's no coal available at that time. So the cost you are going to spend 5 times only for buying the coal. Even India is not having the coal. We are buying from Australia. So this is the right time in which you can bring the other sources so that the amount you are going to spend for producing 1 megawatt farm through the coal route going to be maintained or make it as zero after some time. Okay, gas turbine, all the Mitsubishi they are working on using the ammonia in the aircraft application. It starts with I can say stationary gas turbine plant. Then slowly the idea will be taken for aircraft to burn the ammonia in this. As you all know that how the ammonia systems are working and gas turbine. Simple gas turbine, you have a compressor, combustion chamber and gas turbine. So air is compressed because the aircraft is flying at a height of approximately 40 kilometers from the ground level or something. So assume that the place where there is no air at all. Aircraft is flying in the zone where there may not be any air at all. Or maybe air is available, but the pressure difference is going to be pressure difference. We need a pressure difference to allow the fluid to go inside. The pressure available in the surrounding lower than the pressure available here. So need to maintain the pressure more than the pressure available at the elevation. Further, you are going to use the compressor to raise the pressure so that the fluid will get to move. If your air is not going, you are not going to put in the power in the turbine. You are not going to propel the vehicle. So the compressor is mandatory, but it has a disadvantage. So suppose by producing maybe I can say 1 megawatt power from the gas turbine, 2/3 of the power comes out from the gas turbine is only for running the compressor. Suppose you are producing 100 kilowatt, 66.66%, 67 kilowatt is only for running the compressor. But anyway, we need power for running the gas turbine because there is no grid available at the height of 10 kilometers or 20 kilometers from the ground level. You need to create the power. That power can be used for running the turbine. From the turbine, you need to use the power for electricity, for lighting or refrigeration or other applications, right? So even then we are dropping the power, 2/3 of power comes out from the turbine to run the compressor. There's no other way. We need to compromise for it. Here they are using, I can say, normally the aircraft they are using very oil petrol. Now the ammonia, if it comes into the aviation sector, that means a lot of research is going on across the world. Okay. So with respect to adiabatic flame temperature reaction ratio, there are three different fuels are tried: methane, hydrogen, and ammonia. You can see here the maximum temperature you are going to get at hydrogen. Adiabatic flame temperature, if you maintain the same gas fuel ratio as in that. So the minimum is going to be there for ammonia. This is good for the engine durability also. When the temperature of the combustion increases, right, and it is exposed to the material, the life of the system also goes down. So need to maintain some optimum temperature so that engine is also not going to be compromised, and also the durability of the engine components also. In this perspective, for the same air fuel ratio, throughout the air fuel ratio from 0.8 to 2, you can see here ammonia occupy the lower adiabatic. So lamination, in terms of flame speed also, you can see here hydrogen carries the maximum, I can say, precursor need to do it for the same air fuel ratio. That's ammonia very near to zero. In terms of safety, in terms of compatibility, in terms of life of the engine components, ammonia is going to be better, but only thing is the ammonia is toxic. The leakage, if this happens, is going to give some kind of irritation to the people, those who are nearby. Also, it is corrosive. So the materials, whatever the ammonia is exposed to the engine component, should be prepared in such a way that anti-corrosive materials have to be brought in. It's prone to corrosion not only for copper, aluminium, exposed to rubber also. So you cannot avoid aluminium or copper in the engine component. So you need to go for specialized material which cannot react with it. So here the combustion, you can see here, it starts for this one methane, right? So 0% ammonia is methane. 10% ammonia with 90% methane, 10% ammonia, 20% ammonia, 80% methane. This is called blending. How the diesel and biodiesel blended, how the pyrolysis oil and diesel blended for, right? So to ensure that we are whatever the problem associated with the methane can be reduced by using ammonia. That's the point. That's the thing. But people are not working on it to use the methane completely, going for 100% ammonia. So this is the simple system for engine setup, the proposed engine setup. Anybody want to produce the power stationary power system, they're able to produce the ammonia successfully. This is the minimum number of items are necessary to produce the power from ammonia. We will take this one, the laboratory thing, we will show that how the fuel can be injected, gaseous fuel can be injected. Because we will time permits today, maybe in coming days we can show. So this is the engine. So this I said right, this is the piston, this is the piston pin, the gungeon pin, or this is the connecting rod. So this is the cylinder. So here the intake manifold, exhaust manifold, valves, then the fuel entry in terms of diesel or spark entry in terms of spark plug, some petrol engine, spark plug mounting here. Suppose you are going to use ammonia liquid in petrol, along with that you can put fuel injector. If you want to use liquid ammonia in diesel, along with the fuel injector, you can use spark plug. So this is the by using ammonia, there are several components you need to brought in for the automobile. Suppose you have the older car, I want to convert that car which runs on petrol or diesel into ammonia, you can try that. So other basic items you need for using ammonia in the existing system. I think I can close this one. When you want to use the ammonia in the engine, you can do the emission reduction in the cylinder itself or the after treatment by using a selective current reduction technology. But keeping anything in the exhaust will increase the back pressure. So it will increase fuel consumption. So any emission reduction, if it is possible to do it in the cylinder itself, then we appreciable. If you want to do it in the exhaust, then you are going to create whatever the pressure of the gas comes out. If you want to keep something, you're going to create a pressure. That pressure is more than the pressure coming out. But there's the possibility of gas will goes inside. So in the exhaust valve, the inlet valve, rather than sucking the air, you are allowing the air, exhaust gas to go inside. Because at the end of the exhaust, intake stroke starts. So there's a possibility of dilution of the intake charge rather than fuel and air. That gas also will go into it. So when you are dealing with the after treatment method, you should take care of all those things. Pressure drop across the SCR catalyst system. Okay. The reduction oxides, there are methods are available. You can go do anything, can say either instant or after treatment by various, there are proven technologies are available. You can try that. Life cycle is very important. Actually, all the research comes out so far. People are not focusing on the life cycle part, right? Life cycle analysis of any project is very, very important. If you have, I can say, if you have any idea about writing a paper or some kind of knowledge in getting the life cycle analysis of any project comes out, new projects or the current project you are running, you have a lot of, I can say, possibility of getting projects and also for publication, paper will be easily published by considering life cycle analysis of each individual only, even vehicle you can say, you can catalyst also, every part or combine everything, you can come up with feasibility of the plan by replacing the conventional one, you'll see this first life cycle analysis. Maybe some topics are there in life cycle analysis also, we'll think about. There are some softwares are available that is going to support for life cycle analysis. So one of my student got the postdoc because of this one. He did some part in the life cycle analysis part in his PhD work, and even then it's not possible at NIT. With the help of someone, he has completed. So now, after completing PhD, he was then IIT Hyderabad at the postdoc, and he applied in France, one top university in France. But because of the work he has contributed, life cycle analysis, he got the postdoc. He's going to be there for 3 years in France. So what is necessary? I want researcher to work on it. What is tough in your life? You can try that. You have the future. Thank you so much. We will break for maybe tea is arranged in the thermal lab. We'll go to that. Thank you.